Great. So let me begin by thanking the organizers. It's wonderful to be able to come to a conference after some time and also do a talk. So I'll be talking about, kind of a program of work that I've been carrying out for quite some time now. And this bears on this whole issue of cosmology in the following way. I mean, you've been hearing about how successful cosmology has been on various fronts, but you need to be really worrying about what are the fundamental assumptions that it's all built on. Now, of course, we all really think they are robust, but then you should keep checking. So I'll be talking about one such thing and maybe refer to something else um, on the way. So this is a test of the basic cosmological principle of homogeneity and isotropy. And the reason you should want to test it is because now we have the data to really question it very robustly. Okay, and this is a body of work with many of my students. Not the earliest ones are not listed, but more recent ones and some postdocs here. So let's anyway. So this whole story is on this cosmic screen. That is where you see the cosmic micro background from. I won't really go into details, but I mean, many of you would know that this comes from a universe which is almost 500,000 years old relative to our current age of 14 billion. And what you're seeing is essentially really a plasma screen. I mean, there's plasma at about 3,300 Kelvin. And the fact that if you look at the radiation, it's a perfect black body is a very strong indication that the universe did have a hot early phase. This is probably the one unquestioned evidence that the universe was at least 10 million times hotter than what it is now. And here, what we see close by is what you've been seeing, the structures now. But the question that is always on our mind is a lot of the inferences that we have made about cosmology till date is based on the fluctuations that we see in the plasma screen, not really the plasma screen itself, but the fact that the temperature is slightly different at different directions, the intensity, and also there's a linear polarization pattern. But these are what led to this. And if you really now, most of the success in cosmology has been that we have this picture of the universe at two fairly disparate times. And you want to have a consistent cosmology that takes you from the fluctuations that you see here to the universe now. That's, like a very simplified way of saying where the success comes from. But all that depends on the fluctuations that were imprinted on the plasma. We still don't have a particular model of what created them, but we have very good guesses and they seem to be working very well. So nevertheless, that remains a question. So the microwave background field, of course, had a very successful 3 decades or more, I mean 3.5 decades now. So started with the Cosmic Background Explorer, the Wilkinson Microwave Background, Microwave Anisotropy Probe, and the Planck Satellite. And each of them improved the amount of information that you could get out of the screen. So at this time, most of the intensity fluctuation information has been really mapped out by Planck. I mean, at the scales that we are mostly worried about in constraining cosmology. And there is but still a lot of polarization information that is left. What is impressive is this is from the Planck 2018 results, is to show how fast our understanding of a cosmological model or convergence to the standard cosmological model has improved. This is the figure of merit is just in an inverse of the size of the error volume in this multidimensional phase. And you can say, depending on which one you're looking at, this is the simplest 6-parameter model, and you can keep adding. But nevertheless, what's impressive is there's been a transformation in our ability to pinpoint what is the model of cosmology that works. It may not be the model, correct model, but there is a model that works very well. Okay. And this game is going on. So Planck, although has been very successful, now there are much more sensitive experiments going forward already on the ground. So now, and okay, so I should say that, so this is the backdrop. So, and I'm emphasizing this because when I started researching cosmology, this was not the scenario at all. In the early 90s, we didn't know any of these parameters to any reasonable accuracy. I mean, it's sort of the fact that we know these tell you that we have a working model to stand on and then ask deeper questions. And this is just again showing you how rapid I mean, there have been many other observations which have done this, but I'm just focusing on the cosmological background, various generations, and to show you how quickly we have been able to pinpoint the parameters or various parameters. These are cosmological parameters. And just mentioning the H naught. So, this is, I started well before this. So this thing was, as messy, and there were things piled at these two. So now we have, we are the tensions that we are talking about are, kind of a different kind than the tensions that were there, 30, 40 years back. But we have a standard cosmological model. And the important question to ask is, have we checked every single underlying assumption? And so it's geometrically flat. That is fairly well established. Of course, we have to invoke dark energy, dark matter. Although we are very familiar with it, these are unknown. I mean, we don't know what they are still. And we invoke a primordial power spectrum. And it is always good to question how dependent is our inferences, are our inferences on this. So this is one line of work that I did. I won't talk too much about it, but when WMAP came out, we sort of started a program of deconvolving the power spectrum given a model. And we could see that there were features at low K, that is on the largest scales, but they are also the scales which are cosmic variance limited. So you really can't say too much. But nevertheless, there are some aspects that are very clear. There is a deficit of power at low multipoles or very large angular scales, which still persists at about 2.5 sigma, 2.7 sigma. But on larger wave numbers, which is smaller sizes, scales, things seem to be very, very consistent with the power law assumption. I mean, of course, you can, depending on your taste, you can, kind of make stories out of these, but, broadly, you don't really have too much space. And this is what, that was from our work then, just after the first year of Planck, first release of Planck. And this is from Planck 2018, which basically shows you that with this data, you cannot really say there's an issue with having a power law. Power law is well within what it is, but this is, but our ability to do that has improved dramatically over the generations. You can see from Kobe to now, we sort of fairly okay, assuming that power law distribution. Okay, so what have we achieved? So we do have a standard model of cosmology. Sorry? Can I ask a question? This is a comment. Yeah. This one is we deconvolve using Richardson-Lucy. So initially we used to fix the model, but as we could do it faster, then now we do it over a whole model space. That has been the game that has gone on. So in that, this was in 2014. And after that, sort of, Arman was my student who did it for WMAP 3. And then Dheeraj was a student of Sriram who went and worked with him. So this is a program that they are still carrying on. I have sort of decoupled in the last few years from this. And so this oh, and sorry, I forgot to mention that this Planck thing is a parameter free of a different kind, but this is what the collaboration decided to put out, right? Not our work. So we have a fairly good idea of the universe. Also, the perturbed universe, many of the things that we have assumed seem to have been independently checked. Like, we do know that there's an acoustic phenomena happening, which gives you these baryon peaks. There's independent way of seeing it in the polarization. Then there's a paradigm of structure formations. You see gravitational lens, seeing signal of the CMB, or many other ways in which you see structures growing. Initial conditions, we have a few of the things checklisted, like the kind of initial conditions we require, the power spectrum. But there is one goal that we would like to get to, is to see a gravitational wave background from inflation. This is where we stand. And this is again from Planck 2018, that more or less at the measurements then, which probably have changed a bit more, but all these things are fairly well constrained. When I'm saying that we know that we have checked that these assumptions are correct, they have been, actually quantitatively well checked. Okay, so now let me focus on one of the issues, and I feel that's really a major one. And every now and then there is, some worry about, oh, is it all correct? And because if cosmological principle holds, we can't really go to every location of the universe. I mean, we can do it to a bit, but not really so much. And ask whether the universe is isotropic around each observer. But first, we'll have to make sure that we see a universe, around us. And statistically, the predicate of this cosmological principle is that statistically, all the fluctuations we see should be isotropic, which means the statistics that you create can never tell you what is the orientation of the sky. If I give you a sky map and in rotated coordinates, you should not be able to get any other, a different cosmology. That's a simple way to put it. So there is, this has been, of course, questioned time and again, but what the research program does, we started on, is to find a mathematically well-defined formalism, which was not, targeting looking for a particular kind of signal. So you all, or maybe you may or may not know, but the CMB, if the universe is statistically isotropic, is entirely determined by angular power spectrum, okay, which is essentially the diagonal part of the correlations of the temperature fluctuations. And if there are signatures of any statistical isotropic violations, they lie outside. And there's a very neat way of combining this information into something called a bipolar spherical harmonic spectra, which captures these off-diagonal correlations. And also, since there are, so this is very akin, not akin, I mean, it's exactly angular momentum, total angular momentum representation. If you have two angular momenta in quantum mechanics, you do that. So it's the same thing. The total angular momentum and these two span two different aspects of the map. One spans, like L, this is like a wave number, tells you the angular resolution at which you're looking at the map. This one gives you the angular scale on which you have correlation features in the correlation, right? And this is quite important. So another simpler way to put it is, we have been always measuring the angular power spectrum, but what we showed and we have been doing is that given good data, you can push and get a series of angular power spectra kind of things, but which capture any deviation from statistical isotropy. These are the bipolar power spectra. Okay, so I think I'll skip over this. What do you, intend to look for? So of course, there are big questions. I mean, we're talking about the universe being homogeneous and isotropic, but you can be that, but yet have a direction if the universe is topologically multiply connected. You can answer that, and people have. I mean, Planck has a whole team which looks for this. Then, anisotropy rotation at various times, you could put limits on this from this thing. And then global symmetries. These are interesting to many people where you can, so there is, what I want to emphasize is if you have a thing to look for, we have good data and a method to constrain it, right? If you have any way of looking for any of this. And I'll talk about two guaranteed signals of statistical isotropy violations that are, there. One is extremely good because it sort of calibrates all your methodology, because we are moving with respect to a cosmic microwave background. We do have a direction in the map if you don't go before you correct for it. And then the weak lensing that has been talked about was galaxy weak lensing, galaxy lensed by clusters in front or galaxies in front. But the CMB is also lensed through the Laskin structure, and that that CMB map is statistically anisotropic, and that is being detected by Planck. That signal has been detected to get you the mass that is intervening. Besides that, there are a lot of other reasons you can use this thing, because it catches a lot of observational artifacts. And I'll give you a couple of examples from each of them. So let me tell you what's interesting, because those talks on weak lensing, I thought I'll just recap what we did. What is neat about this formalism? This plot you have seen, the cosmic microwave background photon comes through Laskin structure, gets deflected, gravitational lens. But overall, you can approximate it like a thin one scattering. So this is called, so you'll have a, basically a one single surface from which it's scattering away. So you have the CMB coming, there is something that lenses it. So the direction of the microwave background that you see is not really the direction at which the photon was emitted, right? And this can happen both if because of Laskin structures, as well as if there was a, very strong stochastic gravitational field, a wave field. Okay, these both are valid. What happens is, if you want to picture this weak lensing as now a violation of statistical isotropy, where you take the temperature that you see in one direction as a deflection field, the weak lensing due to Laskin structure is the gradient of a scalar quantity, and the part that comes from anything like a gravitational wave will be the curl of a pseudoscalar quantity there. Okay, and the interesting part is this part is often measured, but just to make sure your things are doing right. And in this bipolar harmonic representation, what we found very neat is these two paths separate out cleanly into something with odd parity and even parity, so that there's no chance if you're measuring one of them, you will pick up any signal from the other. Okay, then let me give you an example from systematic effects. So CMB analysis is done assuming that the instrument that's looking at the sky, is looking at it with a perfect beam that is rotationally symmetric around the pointing direction. If that doesn't happen, you can make errors in, and if you look at the raw maps of Planck or anything, they have to make huge corrections to do that. WMAP had not really looked at that, and when they tried this bipolar statistics on their data in their 7th year release, they found this huge signal. They of course recognized it as most likely coming from systematic effect, but they didn't pin it down. But you can. So a bunch of students and who of mine basically carefully modeled the WMAP beam, made maps with that beam, and showed that you exactly recover the signal that WMAP7 saw. So it's very clear that, and what is important there is this non-circular deviations that you're talking about are at a percent level. But if you look at the signal, it's fairly statistically significantly detected that there is a problem there, right? It's not sensitive. So this is one benefit of searching for this thing. Now let me get to where two things that I'll talk about. There has been always a question about the isotropy of the universe ever since Kobe. So Kobe saw the universe at this kind of a resolution, right? Even slightly coarser than this. And even in the Kobe map, people pointed out that you could see that there are two halves of the sky in where one half had distinctly stronger fluctuations than the other. But W map also, if you reduce it to this, saw that. And Planck also sees that. So this is something that exists. So we were part of Planck to actually address this carefully. And also, of course, as with any interesting possible thing, there have been a lot of theoretical models trying to find out what can create a universe which is lopsided, fluctuations being higher on one side. And people have been talking about these evidences, but these have been all based on very different statistics. So I'll just focus on what we focused on, because what clearly is happening is we don't really know if it is really there. We don't know where it comes from. There is no real good model for it. So in the Planck team, this was modeled phenomenologically. So you assume that the universe, there is a map which is isotropic, but we are in a universe where that map is multiplied by a modulating function, 1 plus m. Okay. And then, of course, it's a function of the sky, so you can decompose it in spherical harmonics, in the bipolar harmonics. And what we looked for is any of the m for capital L equal to 1 to be tried up to 32, deviant from 0. And we found that the L equal to 1 is indeed deviant, but interestingly only if the map on the low resolution map. As you add more high resolution modes, they are statistically isotropic. So it's a very interesting thing that there's a signal which is at about closing on 3 sigma, 2.728 sigma, and then if you're looking at higher multiples, or maybe a better picture of that is you can see that as you include more and more higher resolution modes, this sinks into the cosmic variance. But at the lowest one, it is kind of 2.7 sigma or something like that. What we did as a part of the Planck collaboration is, quantify this anomaly. So you want to know how significant is it? Should we worry about it? And what we've said is it has a p-value of some 0.006, and which means 6 times out of 1,000, this can happen by chance in a random throw of the dice, right? Or the random sky. Okay. But there are much better ways of doing it. And of course, Planck has been doing that for everything else, like the power spectrum and everything are essentially done in a totally Bayesian way, where you're giving the maximum of the posterior, right? So even the map that you see is not the map, it's the most probable map. So you can do that, but this is a slightly difficult problem going beyond angular power spectrum and also looking for deviations from that. But we tackled this with Hamiltonian Markov chain. So we have set up a method by which you could look at a random field on a sphere and probe not only its power spectrum, but also the deviations from the isotropy part. I mean, the non-statistical isotropic part. So this was the paper where we set the method up, and this is where we applied it to this question of, are the fluctuations in the universe lopsided? Okay, and so you took the CMB data. I just wanted to show you that, while what you see often is a very nice full sky map, it has to be masked because the galactic residuals are really strong. If you want to do really scientific analysis. There are other things which also are, break the isotropy in the sense that the map is not as sensitive in every direction. So there's a noise variation. Noise varies on the sky and it has a very typical pattern. If you don't account for that, that will also show up as statistical isotope violation. So we address this question, and I'll cut the story short in terms of to say that if you really looked at the Bayesian odds of this signal happening, it's interesting, but it's not really conclusive. But the odds are 0.25 in favor of a statistical isotopic model. So actually it does not disfavor a statistical isotopic model, but it neither does it strongly favor it, and that is what we found. Okay, so the other place where this is actually questioning the cosmological principle anyway, so it's good. I'll come to a health report at the end. Similarly, in Planck, for the first time in 2013, kind of saw something very interesting, which is the CMB sky as seen from an observer. We know that we are moving in one direction at 380 kilometers per second with respect to cosmological background. That creates what is called the dipole of the CMB. It's hotter here and colder here. And this, nevertheless, also from your special relativity course, you'd realize that for an observer who is moving relativistically, the sky is aberrated. So there's aberration and modulation effect, which makes the CMB sky that you see statistically anisotropic. So this is, of course, an exaggerated view of how the grids, the sphere is kind of getting squeezed in one direction and spread out in the other direction. But this is exactly what is happening. And for Planck, it was just to show Planck collaboration, just to show that this can be measured. We also measured it with our biparticle thing, largely to make sure that our method works, because we recovered that signal. But recently there have been questions about cosmological principle being under stress, because if you measure our motion with respect to distant quasars, which is a fair idea of a rest frame from which you could do that, you find velocities which are far larger than what you infer from the cosmic microwave background. Instead of 380, it's almost double of that. It's actually more than double of that. So we thought we would do a more careful thing with the Planck map and try to recover this signal, first of all, in a Bayesian fashion, as well as with the, to the best possible statistical significance we could. So we put that machinery to work. So let me, skip over all the details. But essentially what happens is, there is an off-diagonal element created in the, so other than the angular power spectrum, there's another power spectrum you can measure when you have a sky which has a Doppler boost. And we essentially measured that spectrum. And you can do that, and you can ask for what is the direction you infer of this from just not looking at the dipole, but just the aberration effect of the CMB. And now I have also a posterior distribution for the speed at which we are moving. We find that we are consistent with the velocity inferred from the CMB dipole. Also, since we have the entire posterior distribution, we can also say how unlikely is it that we are moving much, much faster than that kinematically. Okay, and so just again with the Bayes factor, we are consistent at 7.5 with the CMB dipole velocity, whereas now again, I'm not saying they inferred this value, but if you took that value and say it's all kinematic, then it's a beta of almost twice this, more than twice this, and that is ruled out to the base factor of 10 to minus 11, right? So this is the situation. So in the terms of cosmological principle, first of all, the CMB provides the largest scales on which to ask the question whether the universe is statistically isotropic. There are two, I have talked about two aspects. One is this apparent modulation. The fluctuation seems to be lopsided in the sense 14 times more power in one hemisphere than the other. What we know is, we have now addressed this with a statistics that is not a designer statistics. We have not really, designed it to look for that. It could have picked up anything. We have looked at high multipoles. We know where the signal exists and where it dies. And also with Planck, as a part of the collaboration, we could also show that it's frequency independent. I think I skipped over that quickly, but you see the same signal at different frequencies. If you do the Bayesian thing, and what we did was ask if the signal is falling off with multiples, then what would be the index? And that's interestingly -1, which for people who know about ISW is very interesting. The ISW signal in CMB also falls off as 1/L. But anyway, so those are, so what is interesting is CMB cannot say that that effect has, the best data does not say that, it's isotropic sky. But there are other things coming up. You have the polarization maps coming up full sky, and also the potential maps from, the, mass reconstruction due to CMB lenses. And cosmic rest frame, our analysis shows that very interestingly, at 5 sigma, you detect the signal and it is consistent with the CMB dipole. And it doesn't really, it does question whether, there's any other possibility there, because that's very well constrained now. Okay, thanks. I'll stop there.